Welcome everybody to one more session of the Vibrant seminar. Today you have Rachid Caich from Université Paris-Cité, and he's going to talk about almost sure upper bound for random multiplicative functions. So Rachid, you can start at any point right now.
Okay, thank you very much for the invitation. So yeah, yes, I'm going to talk about almost sure upper bound for random multiplicative functions. So I'm going to give some introductions and some previous works, and after that, sketch of the proof. And if we get some time, I'm going to talk about some open problems. Yeah, so let's start by some basic definitions. So let P be the set of the prime numbers. So we define what we call a Steinhaus random multiplicative function, which is obtained by taking Fp. So we set Fp where P is prime as a sequence of independent Steinhaus random variables, which mean each Fp is distributed uniformly on the unit circle in complex plan. And we define Fn as the product of all Fp power a, where p power a is the highest power of p, dividing n. So it's completely multiplicative functions. And so this model is used to modelize continuous character and Dirichlet character. So for example, when t is random variable distributed uniformly on the interval 0t, so when t large, so n power it's behaves like Steinhaus random multiplicative functions. So it's a really good model to modelize n power it when t is a random variable. And the other model is random multiplicative function is Rademacher multiplicative function, which is obtained by taking Fp sequence of independent Rademacher random variables, and which means each Fp is equal to plus minus 1 with probability 1.5 for each. And we define the Rademacher multiplicative function as the product of all p, so product of p dividing nfp if n is square free and 0 otherwise. So here, just a quick remark. So if n is equal to 0 if n is not square free, and if n equal to plus minus 1 if n is square free. So here we have some resemblance with Mobius function. So Mobius function as well has this character. So it's equal to 0 when n is square free, not square free, and when n is square free is equal to plus minus 1. So in fact, so the first definition, the first introduction of this model, it was by Wintner in 1944 to modelize Mobius function in random world, let's say. Probabilistic remark. So we as we know, so Fn it's so Fn are not independent, which is clear here because, for example, if we take F6 and F10, F6 can be written as F2 times F3, and F10 is, for example, so is equal to F2 times F5, and they share the same F2. So it's clear it's not independent. And this is the big the big problem here. So when we try to understand the partial sum of Fn, the biggest problem here is exactly this dependency between Fn. And yeah, so this is the whole problem. So this dependency. As it's known, so Riemann hypothesis is equivalent to showing the partial sum of Mobius function bounded by x power 1.5 plus epsilon. And so, as I said, so Wintner in 1944, he to investigate the partial sum of Mobius function, he he proposed this Rademacher multiplicative functions as a model for Mobius function, randomized model for Mobius function. And there is some work here. So the first result, it was by Wintner, 1944, who proved that the partial sum of Fn is bounded by x power 1/2 plus epsilon. And here, this bound is almost Schur bound, which means the probability of this partial sum of Fn bounded by x power 1/2 plus epsilon when x goes to infinity, it's equal to 1. This is what means almost Schur bound. And there is some improvement by Harper in 1983, who proved that the partial sum is bounded by Rademacher random multiplicative function is bounded by square x e power a square log x square root log x log x. And we can't bound the partial sum of Fn by square root x e power minus b and square root log x log x. So there is another recent work of Baskin 2012 and Tottenham Vu 2013. They proved that the partial sum of Fn can be bounded by square root x log x power 2 plus epsilon. So and Harper in 2013 he proved that the partial sum can't be bounded by square x log x power minus 5 over 2 minus epsilon. And there is another recent result of Harper, 2021, we established for any function Vx that tends to infinity, we have almost surely so the absolute value of the partial sum of Fn, it's larger than square root x log x power 1 over 4 over Vx for an arbitrary large x, so that it tends to infinity. And so here we can see some resemblance between so this problem and what we call the law of the iterative logarithm. And I'm going to explain how why there is some link between this law and in general case and in the case of multiplicative functions. So first of all, what is the law of the iterative logarithm? So if we take xn be a sequence of independent random variables, and so that taking plus minus 1 with probability 1/2 each. So there is very known theorem that say that the partial sum of xn, so xn here is independent. So the partial sum xn is almost surely bounded by square root x log x. So so this is almost surely bound. And the typical, so this is the first result. There is another result. So the typical size of the absolute value of the partial sum of xn has a typical size as constant times square x. So the ratio between the almost surely bound and typical size of the absolute value of partial sum xn is square root log x. So this square log x. So this is the ratio between. And so let's go back now to random multiplicative functions. So of course we can't apply this law here because of course the Fn are not independent, and but we might think that maybe there is some version of this law that can be applied here. And so Harper in 2017 he proved that the typical size when x is fixed, the partial sum of n less than x of Fn it's a constant time square root x over log x power 1/4. And so this is the typical size. And so by taking this typical size square x over log x 1/4 and multiply it by square root log x, which is the ratio between the almost fully bound and typical size in the low iterative logarithm. So we got square x log x 1/4. So in fact, Harper conjectured that the almost fully bound of partial sum of Fn should be square x log x power 1/4 plus epsilon. Epsilon just to guarantee. So only to guarantee this, there is almost fully bound. And in fact, Mastro Stefano, 2021, so he was a student of Harper, who showed that the partial sum restricted to n that have a prime factor larger than square x is indeed less than square x log x 1/4 plus epsilon. So this bound, it's really sharp, so we can go further. And and our theorem today is in fact so the Harper conjecture is correct. So we have almost fully bound. The partial sum of Fn is bounded by square x log x 1/4 plus epsilon as x tends to infinity. And so before going to the proof, there's another. So this is an equivalent problem. So if we take like xk, the sequence of independent standard complex Gaussian random variables, and we take a partition lambda. So we define the partition lambda as a non-increasing sequence of non-negative integers, and lambda n is 0 from certain point onwards. So, and we define the absolute value of lambda as the sum of the sequence. So we can define a lambda, so sequence a lambda by this identity. So the exponential of the sum k from 1 to plus infinity k over square root k z power k equal to a lambda. So this define a lambda. So and we take an as the sum all lambda that absolute value of lambda equal to n of a lambda, and we define an. So what is interesting of an, it's that this an behaves exactly as 1 over square root e power n.
I don't understand your definition.
Sorry?
Back a slide, please. So how is this defined? I mean, z to the power lambda is z to the power of an integer, and there are different lambdas with the same value. So how is this the definition?
This is a formal series. Formal series. Sorry, I didn't understand like really the questions.
How do you define a lambda?
Okay. So by expanding exponential of this quantity, so the sum, and so we got, so by expanding this sum, so we got like another formal series of z power something, sum of z power something. So, and we got all values that have the same z power. So this is basically.
Well, when I expand that, I get the sum of some constant n z to the n, or in your notation, a capital N z to the n. When I expand the left-hand side, so how do you select little a lambda? Le côté gauche, on a, c'est la somme de A majuscule N, Z à la N, sur un accord. Mais alors, quand vous avez besoin de faire une définition pour le A de lambda, on fait quoi?
So we expand the exponential, okay, and for each power of z, they have some. We got here some polynomial, some polynomial of xk, and finite polynomial of xk. And so a lambda is exactly this polynomial of z of xk. Okay, so I don't know if it's exactly.
I think the question that what natural is to write the right hand side not parameterized by partitions, but just numbers, just sum over n, z to the n with some coefficients. Like why are how the partitions come to the right hand side?
Okay. Yeah, I understand. Okay.
Maybe are related to Bell polynomial or number.
I'm not sure. I have to.
Maybe you can think about this later. I don't know.
Okay, maybe we can talk like after the talk we can discuss that.
I think that perhaps you can sum instead of lambda sum over n, and the coefficients that will appear in z to the n will be that ones that the modulus of lambda equals to n or something like this, right?
Well, yes, yeah, maybe.
This is typically some Bell type polynomial.
I guess I could understand if you were looking at taking the. Actually, I really don't understand, but never mind. Why don't we just go on? I can understand the sum of capital A and Z to the n. I just don't have no idea what this definition is. But let's not worry about it.
Yeah, let's move on.
Yeah, okay. Okay, I see. So maybe we can discuss that at the end. I think I got okay. Okay, so we define an as the sum of all lambda that had absolute value of lambda equal to n of a lambda. And so an behaves like 1 over square root e power n times some k less than e power n of k. And so an behaves like that. So in fact, we have some result based on this resemblance. So the typical size of an it's 1 over log n log n power 1 over 4 for large n. So and this result is done by Sound and Zaman 2022, and this is the equivalent result of Harper in typical size of the partial sum. And there is another result of Caich in 2022 who proved that for any function that tends to infinity, there is almost surely bound, almost surely exists on arbitrary large values of n for which an, the absolute value of an is larger than log n power 1/4 over Vn. So this is the equivalent result of Harper in the lower bound. And we can prove by the same, so by the same techniques that we have the almost surely bound of an. So an is bounded by log n or power 1/4 plus epsilon.
So sorry, I guess what's happening is that Sound and Zaman worked in function fields, and your lambda is presumably something to do with the degree of polynomials. Is that correct?
Yes. In the paper of Sound and Zaman, it was, yeah, there is some, but it was I think it was an example, not really the. It doesn't work in their paper. It was given an example of in number fields, but I don't know if this was like some. But I'm not sure. I'm not sure.
Okay.
I'm not sure. So I have to check. Yeah. Okay. So sketch of the proof. So so first of all, I'm gonna put mfx equal to the partial sum n less than x of fn, and we fix epsilon, and so our problem, so in theorem we it's equivalent to proving that the event a that defined by the absolute value of mfx larger than 4 square x log x power 1/4 plus epsilon for infinity many x, or maybe we have to say x tends to infinity. This event should be hold with probability equal to 0. So proving that, it's exactly proving theorem. So because A, it's just the complement of in the probability space of the event in the theorem. So mfx is large is bounded by square root x log x power 1/4 plus epsilon. And to do that, in general, we split the event A to some subspace, some sub events. So we take XL as a certain very sparse point, and we define AL as a soup of X between XL and XL minus 1 fx over square root X Rx larger than 4, and Rx is just log X 1/4 plus epsilon. So so A is equivalent to lim sup of L as L tends to infinity of AL, and to prove that the probability of A equal to 0, so we prove that the probability of lim sup as L tends to infinity of AL equal to 0, and to prove that we need to prove the sum of PAL converges. So by Borel-Contelli lemma, so we got the probability of lim sup of AL equal to 0, and we deduce that probability of A equal to 0. So now the whole problem is it is reduced to prove that probability of AL is bounded by something converges. So another reduction. So instead of working with X here, we so following low Tenenbaum view proofs, we can reduce the problem by studying the problem in some test points. And so for any fixed, so the lemma, we have this lemma. So for any fixed constant A, there is a constant C0 depending on A and such that by taking xi equal to e power I power 0 c0, the difference, the absolute value of difference mfx minus mfxi minus 1. So this is almost surely bound is less than square root xi over log xi power a. So that's mean that instead of working mfx, we can work with mfxi. And so the problem now is to study this events. Sup over xi between xl and xl minus 1, mfxi over square root xi rxi larger than 4. And so now we have discrete problems. And so let's define what is xl. So xi, we have seen that it's e power I power c0, and xl is e, we put it as e power 2 power l power k. So it's very sparse points. And with this setup, we have log xi is asymptotically equivalent to log xl and equal to l power k when l goes to infinity. Because yeah, xi is between xl and xl minus 1. So yeah. And we define as well yg by find decreasing sequence. So depending on L and verifying some assumptions, so UK should be larger than XL, and log YG equivalent to like YG plus 1 as L goes to infinity, and Y0 less than XI, 1 over log XI. So this YG, so it will be clear soon why we use YG and why there is some awkward, let's say, assumptions. So let's go back to MFXI. So MFXI, we split MFXI to 3 parts. So so the first sum n less than xi and the larger prime less than y0 plus mf1 and f2, and mf1 and f2 is so it's maybe it's let's say a little bit difficult to see that the all sums it's equal to mfxi. So the difference between mf1 and mf2 is so mf1 is equal, so it's same thing as mf2. The only difference here is the PD adic valuation of d here is larger than 2, and in mf1 it's the same thing, but the PD adic valuation of d is equal to 1. So here it's larger than 2, and here is equal to 1. So after that, we manage the sum to be like that. So this is the only difference between MF1 and MF2. Because here is the PD adic valuation of D is equal to 1, so we can put outside the FP the bigger prime, the biggest prime here, and we gather all numbers, all sums here. And so, and the sum from fmf1 and plus mf2, it's give the sum over n less than xi when paid n is larger than y0. And yeah, here this sum here, this means that all factors of d, all prime factor of d are between yg minus 1 and yg. This is what is mean this sum. And so for the first sum, I mean M0f, the first sum when Pn less than y0, so this sum is not really difficult to bound by something acceptable, and it's straightforward. So it's not really complicated. So we just go directly. So we take the probability and we bounded by the sum. So the sup, we bounded by the sum, and we take the probability here, and we by using Markov inequality and some friable techniques, some techniques, let's see, we can get like, so remember that we have y0 is less than xi power 1 over log xi. So this here is just the expectation of mf0 xi power 2 is just the sum of 1 or the sum over n less than xi when Pn is less than xi power 1 log xi. So this gives this kind of, and this gives the convergence of over L of PA0L. So any questions so far here? Okay. So it's not really complicated to prove that PA0L is converged. So it's not really, and so MF2 as well is not really complicated to prove that the sum of the probability of A2L converges as well. So there is some additional technique of low Tenenbaum view, but it's straightforward as well. So the biggest weight is in this sum MF1 to MF1 xi. But here we have some properties. So the expectation. So we first of all we put xp as fp multiplied by this sum, and we define a filtration fp. So it's just sigma originated by the random variables that fq such that q is less strictly than p. And what we can see here, so the expectation of xp such fp, so this conditional on fp, so here we can see that we can assume by conditioning on fp that this part, which is dependent only on fq, where q is strictly less than p. So we can see that we can assume this part as a constant because we are conditioning on fp. So and so here we can like, and we know that the expectation of fp is equal to 0. So the expectation of fp multiplied by some constant, it's equal to 0. So here we got the expectation of xp equal to 0. So which means that xp is a martingale differences. So MF1 is a sum of martingale differences. That's allow us to apply and some consultation inequalities. So the most known inequality it's called Azuma's inequality, and it states as if we take xk, the sequence of martingale difference with respect to some fluctuation fk random variable, so such that each xk is bounded by ak, some constants. So we can bound the probability of the absolute value of the partial sum of xk larger than epsilon by the exponential minus epsilon square over sum of ak square, and which is really a good so exponential bound, which is a good bound. But the problem, we can't apply this inequality here. So if we apply this, we lose a lot, because here so the Azuma's inequality we need here in Azuma inequality a bound for each xk independently from each other. So so by doing that, so we lose this dependency between the sums when p change. So that's why we need another another lemma, so developed version of Azuma's inequality, so which state that if we take Zn, so the same assumptions, Zn is martingale differences, and with respect to some fluctuation Fn, and Zn is bounded almost surely by some constant, so the same assumptions. So, but we have two other assumptions. First, Zn should be bounded by some Sn almost surely bound, and Sn should be what we call predictable process, which means Sn should be depend only on Z1 until Zn minus 1, and not Zn. This is very important assumptions. And the other one, so the sum Sn, the sum of Sn squared should be larger than some constant t. And here, as we see, so here we need the almost surely bound of the sum, not only the so of the sum, but almost surely bound of the sum Sn squared by some t, and we got at the end the probability of the absolute value of Zn larger than epsilon is less than minus epsilon squared over t. And here we treat the whole sum and not Sn each one independently, which is really important. So because when Sn is, in our case, when this sum is small, so the sum of n less than xi over p n less than p, if n is small, the consecutive prime, so if we take this, the sum of the consecutive prime, it's also small because it's so dependent each other. So and by bounding each one independently, so we lose a lot. So this is the very important idea that we should keep it in mind. So now by applying this lemma, so our problem is reduced now to studying the variance of MF1 xi. So it's not really variance, but let's say so our problem is it's reduced to studying the sum over p between y0 yg so the square of n, the sum over n xi over p less than p of fn. So we divide the sum over g now, and the property here of yg is that log yg is equivalent when L goes to infinity to log yg minus 1. And we're gonna see why the log yg should be equivalent to log yg minus 1. So to prove the theorem, so we should prove that almost surely the xi is less than xi over square root log xi. This is our now our new problem. And so the key point here is that that among the terms of the sum of Vxi here, so our Vxi here, so we have a sum over G. The only term that contributes significantly here is when G is Yg is close to Xi. So when Yg is so far from Xi, this sum is so small. And in fact, the number of Yg close to Xi that contribute significantly in the sum, it's so small. It's less than log xi power epsilon over 50 or 4. So let's say over 100. It's also fine. And all this, so all extra factor should be found absorbed by log xi power epsilon. So our problem now is reduce again to study the TLV YG XE XI, sorry, which is so equal to P bar P, or the sum of over P between YG minus 1 absolute value of the sum of Fn. So our problem is now studying the soup of this quantity over the soup over YG and XI. So this is our new problem. Now we the smoothing part. So this is a classical techniques that's used by Harper and Mastro Stefano and maybe before. So we insert some logarithm weights and we split this. We split this part. So this square root. So the sum of square of the sum to two parts. So it turns out that this part it's small, so it can be bounded straightforwardly. So it's not really complicated to bound it by something acceptable. So we left with this part. So this is so the problem basically is reduced to this to studying this quantity. Here, so very quickly, so here we divide this sum to n less than xi less than t, so over t, and here we have n less than xi over p and xi and larger than xi over t. So t is so close to p. That's why this part is so small. So now we convert the integral. So we convert the information of the integral to indicator here. So we transfer the information of the integral to indicator here, and we expand the integral, and yeah, we put it here. So and we gather the information of the integral and the sum here, and we bound this quantity by integral between yg minus 1 and yg of x, sum of p over this two quantity here, mean of 1 over p and this sum square. So we can reduce the integral to yg minus 1, and we get over the 1 plus 1 over x, because the rest of the integral is so small, so we can reduce the problem to studying this quantity. So sorry, I know I have to see. Any questions so far here, or? So now we make change of variables. So we put z equal to xi over t, and so here we put z equal to xi over t, and so we got at the end some this quantity. And we define xi yg equal to xi, integral between xi over yg minus 1 xi over yg of x, sum over p, 1 over p, and multiplied by this by our sum square. And here we got dz over z square. So due to change of variables. And so we can bound this. So the sum over one over p when p is between xi over z and xi over z multiplied by 1 plus 1 over x by 1 over x log yg, and we bound this quantity, so x chi yg by so the x, so the x here go with this x, and we left with xi over log yg. And here we bound this quantity which depend on p by the sup over p. Okay, so now we have a good quantity, but we have to go over this sup, because to get something without sup, to use what we called Gaussian multiplicative chaos. And so to do that, we divide this sum. So the sum here, so the sum of sum over n less than z of Pn and Pn less than P of Fn to 3 parts. So so we divide the sum of Fn when n less than z of Pn P less than and Pn less than P to 3 parts. So the and these 2 parts, when Pn is less than xi over z and Pn larger than xi over z 1 plus 1 over x, and this quantity as well, it's not really complicated to prove that is so small as well. So straightforward by high moments, or we can prove that it's bounded by something acceptable. And the weight of this sum, it's almost the same thing as this sum. And so our quantity xi yg can be bounded by let's say xi over log yg, and here we have something without sup, because this quantity didn't depend on p. So we have something that doesn't depend on p. And before going any further, so in Harper results, so 2017, when he proved the typical size of the sum, he has the same quantity, but he has Pn less than something constant that doesn't depend in anything. And by expanding, so in his article, he expand the integral to 1 plus infinity, and by using Parseval identity, he turns this integral to Euler product, and here he used what we called Gaussian multiplicative chaos, because we have products of independent random variables. So and he proved this, so his results. So now what we have Pn less than something that varies, so it's not a constant. So we can't apply Parseval identity or something like that. So it doesn't. So what we need is to so remember that we need to bound the probability of the sup over yg and xi of s. So here, so to do that, we need to understand this quantity xi over log g integral of square cut, and see if there is some kind of increasing or decreasing in probabilistic term, which mean if there is some supermaterial or submaterial hidden here. And in fact, yes, there is some. So we can, so by adapting a little bit this quantity, we can force it to be supermaterial. So by multiplying by log yg log y0 over log y0 power 1 minus 1 over log minus 1 over lk, which is equivalent to 1. So it's not really it's not a big deal because yeah, it's bounded by constant. So and by expanding to integral, so here Pn is less than j giz, and it takes the same value in this in the same interval. So here giz is equal to xiz, and we take also yg when z is so small, and y0 when z is big. And by forcing by expanding the integral and multiplying by this quantity, we have what we call a supermaterial. So which mean we have some so ygi is a decreasing quantity in probabilistic term. For hi, the sequence of random variable ygi is supermaterial with respect to the filtration of filtration fyg, which means the expectation of yg plus 1 I is at least ygi. And another remark which is really important, so y0i doesn't depend on xi. So with this lemma and remark, we have another lemma which is what I call a two-dimensional loops inequality, and it says that if we have a supermaterial and the x0 k doesn't depend on k, so we have a version of Dubs inequality. So two-dimension because we have two variables. So this is why I call it two-dimensional Dubs inequality. So our problem now is, as I said, is reduced to studying. So this is the unions. It's the same thing as sup. So sup over xi and sup over g of this quantity larger than so this term is just added to guarantee convergence. So it's not really important to understand. And we and as I said, u0i doesn't depend on I, so on xi, and it's equal to I0, and by Parseval identity, so it's equal to 1 over log x0 log y, and so integral plus infinity minus infinity of f0 1 over 2 plus 8 it over 1 over 2 plus 80 square. And f is just the other products for p less than y0, and it doesn't depend as we see on xi. And the last lemma to conclude is so Harper result on low moment estimates. So as we know, Harper proved that if we take this quantity I0, so the expectation of I0 power q, where q is small, it's give so we win 1 over square log x log y0 power q, which is exactly 1 over lk power over k over 3. So here we take an example of q is equal to 2 power 2 over 3. So, but putting all together, so all these results, so we get the convergence of PL. So we split this. So we take the probability of these events, which are what we need to. So we need to prove that the sum of these events over L converges, and by splitting, so by conditioning over S0, and S0 is S0 is an event that is an event defined by E0 less than T1L power 1 over 2 over LK power over 2. So LK power K over 2, and so the complement of this event is rare events, which mean the probability of P0 by Harper result converges, and this by using the Doops inequality, two-dimensional Doops inequality, we get the PT of L less than 1 over T1L power 1 over 3, and by taking T1L equal to L power 8, so we got the convergence of the sum. Yeah, so which proves the conjecture. So yeah, that's it. Yeah, I think I'm stopping here.
Okay. Thank you very much, Rachid, for the nice talk. As I said before, it's a very impressive work, and we are open now to some questions. Does anyone in the audience has a question? Well, I have only one comment to say is, I don't know if you know this, but actually in the Rademacher case, the random variables are pairwise independent. Let's say f of 6 is independent of f of 2. Don't know if you know this.
Yeah.
Yeah. They are pairwise independent, but not treewise independent.
Yes, exactly.
Okay, so I think that if no one has a question, we can stop recording now. And Andrew Granville was he said to me that he has to leave earlier, and he asked